one thing I noticed yesterday, so I sent announcement about the video. Yeah. So when I click the video file, oh, good, it works now. Yeah, it's better. But yesterday, probably for a few hours, when I click this page, it is blocked. Yeah. So then I post the announcement. Yeah. All right. So if it works again, so then it's easy. Otherwise, if you see it's blocked, you just download this file to your local computer hard drive, then open it from your hard computer. Then you can see it. Yeah. If you cannot see from Canvas. Yeah. Sometimes Canvas may have some problem. If you couldn't see it, download. Yeah. Then you open up. Yeah, from your, so that's one thing. Second thing important I want to talk about, remember, today I will assign you the homework assignment number 1. Today, tonight. So then we need to look at our midterm, because this assignment let you do practice on the important computing questions, practice, for the midterm. So then the midterm, I look at the syllabus. I set a date, October the 10th. Then, if we look at our current schedule, I may like to postpone a little bit, because let me show you the calendar. So we are here. So I will assign you homework number 1 today. Usually I give a little more than 1 week. So 1.5 weeks, 1.5 weeks to complete it. Look at here. If we do midterm this time, just 2 weeks from today, then you do not have enough time to do the preparation after I give you the homework assignment back, right? I need to explain the questions. So I want to postpone just another class, give you another weekend. So you have 1 more weekend to study, okay? 1 more weekend to study for the midterm. So let's look at the October month. This is October month. All right. So this whole week you can work, and the due date for the homework assignment number 1, I want to set Monday, this 7th, October 7th, Monday. Because this weekend I will post the quiz number 3. You need to also practice quiz number 3. So the due date for the quiz number 3 is Sunday, October 6th. Because I do not want to put the 2 assignments due date the same day. Okay? The due dates for the 2 assignments should be on 2 different days. Okay? So quiz 3, Sunday, and homework number 1, Monday. Okay, the end of Monday. Then I do grading. So I need about 2 days. I do grading. So on Thursday, I will do review, go through all the homework questions. Okay, so on Thursday, our review session, I do all the homework, explain all the homework questions. All right, so we do not do, we change our original plan on midterm. Original plan I estimate. Okay, because I can only do the estimate, right? But now based on our current, situation, in order to, because midterm is extremely important. So I want to give you a little more time to do preparation well. Okay, yeah. So then, it's better to give you a whole weekend, right? Yeah, it's better to give you another weekend to do good preparation. Yeah. So this whole weekend you do preparation, all right? Then, when you come back, let's do our midterm this day, October 15th, Tuesday. How about that? October 15th. After you spend a weekend to do preparation, when you get back, then we do the midterm. Okay? The midterm the remaining part we do not change. Remember the midterm 25 questions, you do 20 questions in class. Okay? The last 5 questions, relatively hard, I let you do online. Okay? So you when you go home, you can work online. Yeah. Remember, after the midterm, this October 16th, that's the fall break. Remember, fall break time. Fall break time. Fall break time, that's at October 16th. That means October 17th, we won't have class. All right? We won't have class. So you can use a few days to do the last 5 questions at home. Okay? After the midterm, you have a few days. That week, you won't come to the class. Okay? That week, for this class. Okay? For this class, you won't come to this class. Okay? All right. So you work at home. Yeah, I give you a few days. Still, I make the Saturday as the deadline. Okay? So you work through Saturday to complete the last 5 questions. Okay? That's the midterm. Yeah. So let me update the schedule. Yeah. So in this way, yeah, so you need to try your best to do the midterm well. All right? Yeah? Correct. Open book, open notes, and you can even use your laptop. Okay? Yeah, because you do not need to print out our notes, right? Yeah. So too much materials. Yeah. So you do not need to, print out a lot of papers. Use your laptop to look at your notes. All the materials. Yeah. But regarding the using the laptop, a few things you can do, a few things you cannot do. Okay? Yeah. Search engine you cannot use. You cannot use the search engine to find answers. All right? Yeah, the first thing. Second thing, you cannot use communication software to send messages. Yeah. So these 2 things you cannot do. Okay? Yeah. Other than that, you can use a laptop to access online calculator. That's okay. Yeah. Online calculator. Okay. Like a Wolfram Alpha. Yeah, you can use that. Okay. To do the calculation. Yeah. It's legal calculation. Okay. Yeah. Yeah, but 2 things I mentioned you cannot do. Okay. Yeah. All right. Yeah. So that's about the midterm. Yeah. Yeah. So you have a little more than 2 weeks. So any questions you can ask me. Yeah. So we just mid-October. Okay, October 15th. That's the new midterm. Yeah, I will post an announcement, and I also update my syllabus. Yeah. Yeah. Yeah, because sometimes we need to make an adjustment. When I look at a schedule, I feel if I put follow our current plan, you do not have enough time to do the preparation. That's not very good. Yeah. For most of you, it's not very good. So you want to have more time to do preparation. Yeah. All right, yeah. So that's before the class I want to talk about. Then let's continue what we left last time. Recursive algorithm. Last time I gave you a short introduction. So today, let's apply recursive algorithms to solve a few computing problems. And when we work on that, we try to learn the basic thinking on the recursive algorithms. Yeah. Try to get used to. Yeah. So we need to do practice. Get used to the recursive thinking. Yeah. All right. Oh, just a minute. I saw a chat message. Before I start, let me check that chat message. Oh, Zachary, yeah. Is this homework the same? Oh, yeah. Right, yeah. Zachary asked me, remember I put actually I put 12 starred questions already give you, right? In two exercise sets, right? So I copy those 12 questions, right? I do not change. So some of you may already start working on those 12 questions, right? Total 25 questions. The first 10 questions, concept questions, multiple choice, true and false, first 10 questions. Yeah, just like your quiz question, first 10, all right? After first 10, then 15 questions, computing questions. After the first 10 questions, then you will have 15 computing questions. In the 15 computing questions, I already give you 12. Okay? Those 12, they are computing questions. All right? Yeah. You already have 12 or 15 computing questions. And I will give you 3 more. Okay? 3 more. Yeah. Because some topics I didn't cover. Yeah. For example, the inversion I didn't include. So I need to give you 3 more questions about inversion. Okay? Yeah. So then you will have total 15 questions. Yeah, but 12 questions already in your hand for a while. All right? Yeah? All right? Yeah. So that's the answer to Zachary's question. Okay? All right? Yeah. Yeah, but, yeah, since I look at the message, yeah, so, the problem, I need to restart my PowerPoint slide. Yeah, so that's the problem. I have to end it first, then I restart it. Otherwise, my remote control does not work. Yeah. All right, change my pen color. All right. Okay, yeah, let's start. Yeah. Problem number 7, calculate the factorial. Yeah. So you know the formula, so you can, usually factorial is a large number. Yeah. So you may like to use a calculator to do the calculation. Yeah. But here, our interest is not at the answer of the factorial. Our interest is how to use the recursive thinking to understand this simple computing problem. It's very simple. Yeah. But when we start, we want to use a very simple example to understand the recursive thinking. Yeah. So that's the main point, the starting point we want to learn. Okay. Yeah. The question, given a non-negative integer n. We need to find its factorial, n factorial. So you know the definition of the factorial, right? Yeah. So n times n minus 1 times n minus dot dot dot. Okay. Yeah. Consecutive integers. Yeah. And the last one is 1. Okay. Yeah. Is 1. But here there is a special case. Yeah. Because for the condition, we only say it's a non-negative integer. That means 0 is included. 0 is in n greater or equal to 0. So we include 0. That means we need to know what is the 0 factorial. Yeah. Yeah, because if you look at from the formula, it looks like it does not cover the 0 case. Yeah, but we need to extend it to cover 0. Yeah. Yeah. The original formula does not cover the 0 case. So we need to extend it to cover the 0 case. Yeah. Here, when we use the recursive thinking, so we can naturally do the extension to cover the 0 case. All right, so method 1. Method 1, iterative. Well, iterative. That's easy, yeah, because from this formula, yeah. And so here, if we use the iterative case, we need to assume 0 factorial equals 1. Yeah. So here, think about this condition here. Does it make sense? Does it make sense to assume 0 factorial to be 1, not a 0? 1, not a 0. Yeah? Yeah? That may not be very easy, not quite intuitive. For many of you, this assumption may not be quite intuitive, right? Yeah? Because when you see 0 and you do multiplication, by your intuition, it looks like, should be 0, but actually should not be 0. It should be 1. Yeah. So why? How to see it? Yeah. Later we will see it. Yeah. All right. Yeah. So we will justify it later. Yeah. All right. Yeah. The implementation, we just use a for loop. Okay. Yeah. Yeah. So here I do not need to get into the detail. Let's apply method 2, recursive algorithm. Yeah. So in our method number 2, we need to reshape it. Yeah. Yeah. Because in order to apply the recursive algorithm, we need to modify our problem, modify the structure of this problem to make it fit in the recursive algorithm frame, okay? Fit into it. Yeah. Yeah. All right, so here we need to work, yeah. Do the manipulation on the structure of the problem. All right. Yeah. So here, one typical problem-solving approach. So here I want to, because this recursive thinking is related to a commonly used problem-solving approach. Yeah. So let me explain this divide and conquer approach. Yeah. So that's a, very important problem-solving approach. Yeah. So here we need to use this problem-solving approach. Yeah. But our next module number 4, the whole module, we will learn divide and conquer. Yeah. Yeah. Module number 4, divide and conquer. Yeah. So we will learn more about divide and conquer approach. Yeah. All right. So here, yeah, in order to reshape it, in order to change the structure of this computing problem, we need to do divide and conquer. Okay? Divide this problem to some smaller problems. Then conquer those smaller problems, then after we get the results of, or the solutions of the subproblems, then we try to get the solution of the whole problem from the solutions from the smaller subproblems. That basic idea. Okay. All right. Yeah. So when we work on a problem of the current size, so here we understand the problem size. So what's the problem size? N. N is the problem size. Okay. This N number is the problem size. Yeah. So here, every time we consider a problem of current size, okay, current N, because this N is a variable. The value of N variable may change, okay? Yeah. Could be larger, could be smaller. So the value of N can change, and when we change the value of N, we change the problem size. Okay? Yeah. All right, so this is our understanding. Okay, yeah. All right. Assume that the problem of a smaller size has been solved. Yeah. Yeah. When you work on the current problem size, so here, this is the main difference of the recursive thinking. Main difference. The main difference is when we work on the problem of the current size, we do not assume we start from scratch. Okay? We do not assume we start from scratch. We assume that we have some previous result. When we get to this point, we assume we already have some results from previous problem sizes we can use, not from scratch. We have something we can use. That's the main difference about recursive algorithms and iterative algorithms. Iterative algorithm, we do not assume that. Recursive algorithm, because we know we can do recursion. Recursion means the current computation result relies on the previous computation result. That's the recursion, right? Relies on the previous one. That means you can assume you have the previous one, right? Yeah. So here we assume that we have some previous solution we can use. So we can build up the solution to the current problem size to a solution to the previous problem size. That's the main difference, the key difference. Okay, all right. Yeah, but after you make that assumption, your goal is to find a solution of the current problem size. So there must be a gap between those two solutions. Okay, solution to the previous problem size and the solution to the current problem size, there must be some gap between them. So step number 3, you need to fix the gap. Okay? How to fix the gap? You need to derive some recurrence relation to fix that gap. Then you're done. Okay? That's the whole procedure doing recursive algorithms. Here, let's assume this is the model, okay? Model of our recursive algorithm. Let's use the factorial question, problem, and make it fit into this model. So we can practice on this factorial question. Yeah. All right. Now, let's do it. Divide and conquer. The first step, we need to divide somewhere in this problem. Okay? Yeah. Yeah. Cut it. Yeah. split it into two parts, the problem. Yeah. Before we do the splitting, yeah, let's introduce a function. Yeah. Yeah. Use a function to represent this factorial. Capital F of n denotes the factorial notation. Okay? Yeah. Because after we have this function, then we can do the recursion, right? Yeah. If you don't have a function, then you cannot do the recursion. Yeah. So here we need to define a function capital F first. Yeah. All right. After that, then we do divide step. Yeah. So here we do this way. Okay. We draw a vertical line to separate the last multiplication operand and cut it off from the computation formula. Yeah. After this divide step, you can see we split original problem to two parts. Split our data. Yeah. The data. Yeah. So these numbers, they're our data, right? We split our data into two halves. Yeah. The first half, it contains n-1 data items. The last one contains only one data item. Yeah. So the divide step. Then, how to find, yeah, because we need to build our solution of the current problem size, f of n, that's the solution of the current problem size, on top of the solution of the previous problem size. So what's the solution to the previous problem size? That's this part. F of n minus 1, that's the solution or the function value of the previous problem size. N minus 1 is the problem size. Okay? The previous one. Yeah. So this f of n, its result is built on top of the result of f of n minus 1. Okay? Yeah. But there is a gap, right? There is some gap between f of n minus 1 and f of n. We need to fix that gap. The question is how to fix that gap, right? Yeah. From the formula, how we break it. So we put things together. To fix the gap, we have this new formula. Yeah. Although this new formula is equivalent to the old formula, but we see a new form, right? Yeah. The original formula, there is no recursion. This new formula, there is a recursion. Yeah. So this is a recursive version of the factorial formula. Yeah. F of n equals f of n minus 1 times n number. Yeah. So that's the recurrence relation. So we derive this recurrence relation. Then we can write our implementation based on this recurrence relation. Okay? Yeah. Although here, if we write it, if our method number 2, we use this recurrence relation to write our program, implementation program. If we do comparison with method 1, which one do you think would be faster? Here we have two methods. Method 1, method 2. Method 1, iterative method. Method 2, recursive algorithm. If we implement these two, based on what do you learn from introduction? Last class, I did an introduction. Based on what do we learn from the introduction? Which one do you feel should be a little faster? Yes, that's correct. Iterative, we do not need to maintain a stack, right? This one, you may need a stack. That stack could be very deep. Think about if you calculate factorial of 1 million, how deep is the stack, right? If we use the iterative method, even we calculate factorial of 1 million, then there is no stack to use, right? Yeah. So we only use very little memory. This one we use large amount of memory. So that's the reason. Yeah. So this is worse than the first one. The reason we do here is we want to practice our thinking, right, for education purpose, but not for the real world. Real world, nobody wants to implement in this way. Okay? Yeah. Yeah. Just I try to emphasize this point. Yeah. This point. Okay? So do not get wrong. Okay? Yeah. If you switch your implementation, yeah, because sometimes you need to calculate factorial. If you switch to this, then too bad. Very bad. So you add an unnecessary deep stack. That's bad. Okay? Try to avoid it. Yeah. Yeah. All right. Now, because here in this formula, we see n should be greater than 0, then this formula is meaningful, right? Yeah. Otherwise, everything times 0 is 0. You get 0, right? You don't want to get 0, right? Yeah. Yeah. So here, now let's answer this question. How to see 0 factorial equals 1? Yeah. From this formula, we can see it. Yeah. Why? Yeah. So let me rewrite this formula in this way. Yeah. F of n minus 1 equals f of n over n. Because n greater than 0, we can write this way. N here never be 0, right? So we don't worry about the numerator, if the numerator equals 0 or not. The numerator never equals 0, right? Yeah. So f of n over n equals f of n minus 1, right? Yeah. Yeah. It's correct, okay? Then let's plug in. Let us plug in n equals 1. It should work, right? N equals 1. Yeah. The left-hand side, f of 0. The right-hand side, f of 1 over 1. F of 1 over 1. Is it 1 over 1? We know f of 1. 1 factorial is 1. Okay? 1 factorial over 1 is 1. But left-hand side, f of 0, is it 0 factorial? By definition, yeah. At least we can do the extension based on this formula, right? Yeah. So we want to extend the definition of factorial to cover n equals 0 case. And based on this formula, and we can do that extension. The extension is we make 0 factorial equals 1. That assumption, this is assumption. This assumption is compatible with this formula. Compatible. Okay? Yeah. All right? If the assumption is not compatible with the main formula, then your assumption is wrong. Right? So here, the assumption is compatible with our main formula. Yeah. Yeah. So it must be correct. Okay? Yeah. So that's the way we see why 0 factorial equals 1, not 0. Okay? All right. Conclusion. Yeah. So we solved this problem. Conclusion is, yeah, although we do not say this algorithm is efficient. Yeah. So this method number 2, it's not efficient. Yeah. We do not say that. But here, it is an interesting way to solve problems, right? Yeah. From this experience. Yeah. This is a, interesting method. Yeah. Maybe in future, it could be useful. In future, it could be useful. Yeah. Yeah. All right. So we'll finish our problem number 7, factorial problem. Yeah. Next, 8.2. power of recursive algorithms. Yeah. Now the question. From the previous problem, you know, sometimes the recursive algorithm is not efficient. Yeah, because that deep stack problem, right? That huge deep stack. And I mentioned last time, if your stack is too deep, you may run out of your memory. Then you may have a runtime error. That runtime error is called a stack overflow. Stack overflow runtime error. So your program terminates. Right? Yeah. So you need to fix that problem. The runtime error. Usually runtime error is harder to fix. Okay? Harder to fix than a compile time error. Compile time error, you have some syntax problem you can fix immediately. But runtime error, when you write your code, you do not know it. Okay? When you run it at runtime, you get error. You need to figure out what's the reason. Because many students, when they see stack overflow, they do not understand what's the meaning stack overflow, right? What's the meaning? How do you fix it, right? Yeah. Here we know the meaning of stack overflow. That means your stack is too deep. Yeah. How to fix? Can you make your stack shorter? Can you use some special way to reduce your stack, the depth of your stack? Okay? Or can you store some intermediate results somewhere to reduce the depth of your stack, right? Then you won't have the overflow problem. Yeah. Think about that. Here you know the reason, so you try to figure out some way to reduce the depth of your stack. How about when you do computation somewhere, you store the intermediate result. Before you hit the stack overflow, how about we store the intermediate result somewhere? Okay? Then we start a new stack, but we can build, the starting point is the intermediate result. How about that? Then the stack will be not that deep, right? Yeah. Because every time after some computation, we store the intermediate result. Then we start a new stack, then build up, do more computation, and store another intermediate result. Keep doing things like this, although a little slower, but we can reduce the depth of the stack. Okay? We can avoid the stack overflow, right? Yeah. Here, just give you the idea. Okay. Think about that. When you have the stack overflow problem, think about this way to solve your stack overflow problem. Okay? Yeah. All right. Now let's work on this 8.2 topic. Power of recursive algorithms. Yeah. Let's continue our discussion on the deep stack problem. Yeah. So the question is, since the stack, when we apply the recursive algorithm, the stack, there is some, depth, right? Depth of your stack. Okay? Yeah. So, yeah. All right. So that's the drawback of this method. Right? You need to consume more memory. Yeah. So the question is, why you do not want to throw away the recursive algorithm? You still want to keep that recursive algorithm as a problem-solving tool in your toolbox. Problem-solving tool in your toolbox. Why you still want to keep that tool? That tool has the stack overflow problem, potential problem. Yeah. Yeah. So you do not throw away. You still want to keep that tool because there is one big advantage of that tool: power. It is powerful. It is very powerful. So we want to take advantage of the power of this recursive algorithm. So this subsection 8.2, I want to show you that power. The power is in problem solving. The meaning of power here is it's a very strong problem solving method. All right, let's look at the problem number 8, power of Hanoi problem. So it's an interesting puzzle problem. Yeah. So look at the diagram here. First, some of you may play this puzzle before. Okay. Here, let me refresh your memory. Okay. Yeah. Explain the rules, how to play this puzzle. Yeah. The rules. Yeah. In our first example, let's use the 3-disc version of puzzle. Here you see there are 3 discs. Yeah. Of different sizes. Smallest, the middle size, and the largest size, one in the middle, yeah, mid size, yeah. You need to follow the rules. There are 3 rules. Otherwise, not fun, not interesting. Okay? So you need to follow the rules to make the problem, make the puzzle more challenging. The first rule. What's the first rule? Only you move the discs from one peg to another peg. Okay? Where you have 3 pegs. Yeah. Beginning peg, destination peg, and the temporary peg you can use, to help you arrange all the discs. Yeah. All right. So the first rule, every time you can only move 1 disc at a time. Yeah. Rule number 2, a disc cannot be placed on top of the smaller disc. You have to follow the disc size order. The larger size should always be lower than the smaller disc size. If you look at one peg, okay, for each peg, when you stack several discs, you should follow this rule. Yeah. The smaller one should always be on top of larger one. Okay, you cannot change the order. Okay, put a larger one on top of smaller one. That's the violation. Okay, so this is rule number 2. Rule number 3. All discs must be stored on a peg except while being moved. That means you cannot place any disc on table. Okay, not on any of the 3 pegs. You place some of the discs, arrange them. You have a lot of space on table, so you arrange on. No, that's the violation. Big violation. Otherwise, it's too easy, right? Yeah, not challenging. Yeah. So you cannot place any disc anywhere other than these 3 pegs. Okay? Yeah. So other places you can. Yeah. You cannot. Yeah. All right. If you follow these 3 rules, then even solving this 3-disc version of puzzle not that easy, right? Yeah. If some of you did this puzzle before, yeah, then it's not hard. Yeah. But if this is the first time you play this puzzle, it may not be that easy. Yeah. So let us solve this problem. Yeah. Okay? Yeah. But our goal, yeah, although here I use the 3-disc version puzzle, but our goal is we want to solve n-disc version, the general n-disc version, yeah, not 3. Yeah. 3, yeah, because that's easy to see. we can do experiments on this 3-disk version. If n equals 10, we cannot do 10-disk experiment, right? Too difficult. 10 disks. Yeah. Too many moves. No, we cannot handle that many moves. Yeah. All right. Yeah. All right. Analysis. How to solve the general problem n disks. Yeah. That's our goal. Okay? Yeah. So this is our goal. Yeah. All right. So how to find a solution of this general version? Yeah. Yeah. Here. Recall a strategy we learned before. So here I want to review that problem solving strategy. Yeah. Yeah. Very effective. Yeah. But if I do not emphasize that strategy, so you may not be aware of it. Yeah. So when we have this situation, when we solve the problem, the general problem is hard, n-disk. We don't know how to start n-disk problem. No. So remember, we had experience before for situation like this. We do experiments on relatively small problem sizes. Okay? On small problem, on the simplest problem sizes, we start. We do experiments. When we start, when you do your experiments, we try the simplest cases. Here, we apply that strategy. Okay? Work on the simplest cases as the experiments. When we start, can we look at n equals 1 and n equals 2? n equals 1 is trivial, right? You just one move from the starting peg to destination peg, you're done. That's trivial. How about two disks? Also easy, right? The top one you put on the temporary peg, middle one. The middle one temporary peg. Then the bottom one you put it on top on the destination peg, right? Then you move the top one to the destination peg. Okay? n equals 1, 2, both very easy. Yeah. So now you should have some confidence. Okay? Yeah. So let's try n equals 3. Yeah. Now, we increase the problem size from 2 to 3. All right. But when you work on problem of size 3, can you assume you already have the solution of size 2? The problem of size 2, so, because you just solve it, right? You just solve the problem of size 2. Yeah. So that is, you can use that as the stepstone, right? Yeah. You already get there, right? Yeah. So that place you can use as a stepstone to help you move further. Yeah. So you want to move further, yeah, but you're halfway already, right? Yeah. So that problem size 2, that's a stepstone halfway. Okay? So you can make that as the starting point, right? That one, that stepstone is a new starting point. From there, then one more step, you get a size 3 solution. Just one more step, okay? That understanding, okay? That kind of recursive understanding. That's the recursive understanding. Yeah, yeah. So you build a lot of stepstones, okay? Yeah. Extend the solution paths by a sequence of stepstones. How about that understanding? Okay? Yeah. Not just the one jump, you reach your destiny. That's too hard, right? That one big super jump. Oh, Yeah, you're not Superman, right? So you cannot make that long jump. But we build a sequence of stepstones. Yeah. So every time we just make a modest jump. Okay? Stepstone by stepstone. That's the recursion idea. Okay? Yeah. All right. Recursion. Yeah. Now, n equals 3 is not trivial, but we can use this recursion idea so we can understand the solution. Yeah. All right. Here, let me use the diagrams, a sequence of diagrams, pictures to show you step by step how to solve this three-disk puzzle problem. All right, let's start. Our step 0, this is our step 0. Before we make any move, the state is this one. Before we make any disk move. Yeah. The first disk move, the top, the smallest disk, first one, yeah. Move it to peg 3, okay? Peg 3, yeah. Yeah. Why you move peg 3, not peg 2? Yeah. Because peg 2, we want to move the middle one. The mid-size disk. The second move, the mid-size disk, we place it on peg number 2. Yeah. Then the smallest disk we can place on top of second smallest disk. Okay? Yeah. So move number 3. Then our destination peg is empty. Yeah. Our destination is empty. So it's legal, we move our bottom, the largest disk, to the destination disk. It's empty. Otherwise, if there is a disk there, it's not legal to move the largest disk to the destination peg. Yeah. Now it's legal. Yeah. But here you can see, because we move top 2 disks to peg number 2, is it a solution of P of 2? Is it a solution of problem size 2? Yeah? Yeah, because we move 2 disks from one peg to another. That means we apply solution of the puzzle problem size 2. Okay? Yeah. Yeah. So we see that. Yeah. We apply that solution. All right? Yeah. All right. Continuation. Yeah. Yeah. Next step. Largest disk. We move it to the destination peg. Then, after that, we need to move these 2 disks onto that destination peg. Is it another solution of P2? P of 2 solution? Yeah? Because you move 2 disks, top 2 disks. Okay? Yeah. So that means you need to apply another solution of smaller previous problem size. All right? Yeah. So move number 5. Move the smallest disk back to the beginning disk. Then the middle one, this time you can move it on top of the largest disk on peg 3. Then the last move, the smallest disk from peg 1 to peg 3. Then you are done. Okay? So you get a solution. Here you can see after 7 moves, after 7 disk moves, you find the solution of this 3-disk puzzle. And in the solution, you can see you apply the solution of the smaller problem size, P of 2, twice. not at once. Okay? Yeah. Before you move the bottom disk, you apply once. After you move the bottom disk, you apply second time. Then you get the whole solution. Think about that whole process. Okay? All right. After you understand with this new experiment, this is our new experiment on 3 disks. After that, we feel we have the sufficient experience. We can do the extension to the general n-disk case. N-disk case. All right. Now, let us work on the n-disk case this time. Yeah. We use the disk 3, but in our thinking, we need to think the general case. This time we have n disks, not just the 3 disks. This time we have n disks. Yeah. All right. This time, because we have the important experience from the 3-disk solution, then it won't be that hard. We only need to modify our 3-disk solution. We can get an n-disk solution. All right, so let me just modify the old diagram. This time, let's imagine we have n disks. Yeah. All right. Yeah, but this time, we need help from recursion. Otherwise, how do you work on n disk case directly, right? If you do not use recursion, think about if you do not use recursion, how do you work on the n disk problem? No way you can work on n disk problem, right? Yeah. All right. So here, now, let's do some preparation before we work on this n disk solution. Now, one important thing we can do, we can assume the solution to n-1 disk already available. Can we assume that? When we work on the n-disk puzzle problem, can we assume the solution to the n-1 disk solution already available? Think about that. If you can assume that, then we only need to do the gap part, right? There is a gap. Solution from n-1 disk and solution to n disk. Yeah. 2 different solutions. There is a gap. We only need to work on the gap part, right? Yeah, that's much easier. Okay? Otherwise, if you need to move from the disk 1 through disk n, too much work. Too much work. Yeah. Here, if we use our step stone understanding, yeah, we have a sequence of step stones. Okay? Because when we build, problem size 1, we put 1 step stone. Problem size 2, another step stone. Problem size 3, we just did it. So we have a step stone corresponding to problem size 3, right? With that step stone, can you get a solution of size 4? Size 4, yeah? Because you apply size 3 solution twice, right? Before you move the bottom disk, you apply size 3 solution. Then move bottom disk, then apply another size 3 solution, you get a size 4 solution. So that's another step stone. Use that, can you get a size 5 solution, size 6 solution, and so on. So now you have a long sequence of step stones, and the last one, this is our last step stone, right? Yeah. n-1 size solution already available. Okay? Yeah, based on our, recursion. Yeah. Thinking, recursive thinking. Okay. Then we only work on the gap part. Yeah. Let's work on the gap part. Okay? So when we start, this time we imagine this stack of disks. There are n disks in the stack. Okay? Yeah. Although you see 3, but you just imagine there are n disks, okay, in that stack. All right. Now, our goal, we need to find a solution P of n. P of n, okay? Moving the whole stack to the destination peg. Yeah. So for n disk puzzle problem, you only use 3 pegs, okay? Not n pegs, right? Not n pegs. N pegs too easy. Yeah. So you must use 3 pegs all the time, okay? Even the problem size is very large, you always use 3 pegs. Yeah. All right. So then, first, let us solve the problem. Yeah, because this is our assumption. We can apply that solution first, right? Yeah. That's our stepstone, last stepstone. Okay. We can use that. Okay. Yeah. All right. So that one, we apply the solution P of n minus 1. So we make this, okay? When we apply P of n minus 1, we place the top n minus 1 disks on peg 2. On peg 2, okay? Yeah. All right. Then the bottom peg, move the bottom peg. Oh, sorry. Yeah. Next, move the bottom peg. After that, another P of 2. P of n minus 1. Another P of n minus 1. Then we get our final P of n. How about that? Okay? Yeah. Similar to our disk 3 disk solution. Similar. The structure-wise, similar. Yeah. And we only work on the gap part. Yeah. So from this example, you can see how important is this recursive thinking in our problem solving. Using this recursive thinking, we can solve some very hard computing problems. Here you can imagine, without using recursion, how can you solve this n disk puzzle problem? No way, right? Without using recursion, there is no way people can solve this n disk puzzle problem. Okay? Yeah? All right. So that's the point I want to convey, the power of recursive algorithms. That's the biggest advantage of this one. And the reason we don't want to throw away this tool from our toolbox, because we really need its power in our problem solving. All right. Yeah. The last thing I want to do here, I need to write the pseudocode. Yeah. So the implementation, we need to write a pseudocode of that recursive function. Yeah. Input and output. Yeah. All right. So this is the pseudocode. Okay. So we create a void function called a move disks. Move disks, we need to pass 4 integer parameters. The first one is the problem size. So that's our n number, the problem size. Okay? Yeah. Then the next 3 parameters corresponding to the numbers of the 3 pegs. Peg 1, peg 2, peg 3. Yeah. Here, peg 1 called from peg. Peg 2 we call the to peg, destination. To peg means the destination. Yeah, probably the peg 3. Yeah. The destination peg, okay? Yeah. Then the temporary one, temp peg. Yeah. So these 3 peg numbers will pass as 3 integers. You can use 1, 2, 3, okay? Or 1, 3, 2. Yeah. because the from one corresponds to our peg 1. To peg, that's the destination peg, that's our peg 3. Okay? Temporary peg, the middle one, peg 2. Okay? Yeah. 4 parameters. Then, and the disk number greater than 0. If it's 0, nothing. You don't need to do anything, right? Yeah. So we are, at the beginning, we check the disk number should be a positive integer. Yeah. Then we do recursion. Yeah. We do the main steps. Yeah. The first step, this one is the solution of n minus 1, right? P of n minus 1. Move recursive function call. Move disks n minus 1, then we need to use the appropriate peg number. Okay? The from peg 1 to temporary peg as the destination peg. The middle, the one, this temporary peg, because this is the destination, right? Yeah. So we make the temporary one as the current destination. Yeah. Then the destination one as the temporary peg. Okay? All right. After that solution, we move the bottom disk. Yeah. This is the simulation of the bottom disk. This is the simulation. Of the move of the bottom disk. Okay, simulation. Yeah, yeah. So this is the sequence. So this example I borrowed from your data structure class 2250. Yeah. So I taught that class once before. Okay. Well, probably twice before. Yeah. So I borrowed the pseudocode from that class. Also, the diagram I also borrowed from that class. Yeah. So here, we print out the output as the simulation. Yeah. You do the move. Yeah. Then, after that, you make another recursive function call, and we apply this n minus 1 solution again. This time, we need to change the peg numbers. Okay? All right. Peg number 2, we use it as the starting peg, and the destination peg is still the destination peg, and the peg number 1 as the temporary tag. So then, you apply your previous solution again, you complete the whole solution. See? For such a difficult problem, your pseudocode is so simple. Your recursive function definition is so simple. And even when this n disk size number is very large, let's say 100, you have no problem to solve 100 disk puzzle problem, right? Yeah. Plug in that 100. Yeah. Yeah. The problem is, your output is super long. Yeah. Super long. You have to kill it. Yeah. Because it generates output forever. It never ends. Okay? If you plug in 100, never ends. I cannot imagine how long you need to wait. Extremely long. Yeah. Later, here, how many moves we need to do if we have 100 disks? Yeah, I will answer that question later. That question, yeah, we will solve it later. Okay, how many moves if we have 100 disks? All right, yeah, let me stop right here. Yeah, so we just finished part A, so we do not start part B today. So part B next time.